Let's talk about mechanisms in chemical reactions. We use these to keep track of the flow of electrons, and they'll move from areas of high electron density to areas of low electron density. Let's use this acid-base reaction as an example. Here we have hydroxide ions, and it has a full negative charge. But if we move over to the hydrochloric acid, or HCl, we'll notice that there's going to be a partial negative charge on the chloride and a partial positive charge on the hydrogen. Now, when we draw a mechanism, we'll draw from high electron density to low electron density. So here's the low electron density right here on the hydrogen. And we'll use a double-headed arrow to indicate that there are two electrons moving during this process. So we start here, draw from that negative charge over to the hydrogen. Now, if we just simply add 2 electrons to this hydrogen, that will be too many electrons. So we'll need to move some from the bond in between here over to the chloride. And we'll explain the reaction for the reaction between hydroxide and hydrochloric acid to make water and chloride. Now, you may notice that absent from this is any spectator ions, such as sodium or potassium or some other whatever we wanted to use for a base. Let's pick sodium. And sometimes we'll just leave those off to simplify the mechanism. Just because we're leaving it off to simplify the mechanism does not mean that we can just grab a bottle of only hydroxide, though. We will have to have a counter ion to go with it. It's just floating around in the solution and not interacting with anything else, so we can ignore it for here. And let's talk about that a little bit. Let's simplify some of these areas of electron density so that we can make our mechanisms a little easier to read. So right here we have this alkoxide, which is the sodium plus methyl and then the oxygen here. So sodium methoxide is what this would be called. Well, we could ignore this sodium to make this a little simpler in our mechanisms. So let's write out what we would actually use in the mechanism. And we'll have a negative charge there because we're removing Na+. And often we'll write the negative charge inside of a circle just so it's not confused with our shorthand notation of for carbon bonds when we're using that. We have N-butyl lithium, and we can simplify that one down by removing the lithium. Now, this is kind of a neat case because we'll have a negative charge on carbon, and a lot of times carbon would have a positive charge. But when we're including these organometallic reagents, we can actually get a negative charge on carbon. And that can have important synthetic applications. Anyway, we've simplified down this to indicate that there's a lone pair left on that carbon and a negative charge as the result. This is a little easier to draw in mechanisms, and it can explain some of the reactivity. Now let's look at this Grignard. We have an aromatic ring here, so we'll draw that. And we'll remove the magnesium bromide because this part is the spectator portion. So we'll have a lone pair right here on that carbon and a negative charge. Try to be careful when you're drawing these, and I will too, so that they don't get too close to each other, but still are clearly associated. because it's important to note that there's a negative charge here, but we don't want our drawings to get too messy. Now, just because we're ignoring a lot of the spectator ions often when we're drawing mechanisms does not mean they're not important. In fact, the reactivity between these two species is quite different, and not just because this one is an alkyl chain and this one's aromatic, mainly due to this their organometallic portion, the metal right here or there. Organolithium reagents are much more reactive than their Grignard counterparts. So, while we can ignore things for drawing mechanisms, we do have to keep in mind what they came from, just so that we can keep track of the reactivity that we'll see later. Now, up here I drew some partial positives and partial negatives, and those are important to identify. So let's just look at acetone real quickly. And identify the regions that are important. Now, right here we've got a carbon that I often will not draw, or kind of draw it as an afterthought, so keep that in mind. And we have an oxygen. And of course, the oxygen is more electronegative, so we'll have a partial negative charge here, and we'll have a partial positive charge down here by this carbon. And when we're drawing mechanisms, we'll kind of try to keep that in mind, that if we had one of these reagents here, any one of these, a potential attack point would be that carbon right there. So that way we can think about how we're going to draw a mechanism and what would attract these negative charges the most. So, drawing all of those Lewis structures and keeping track of where our electronegative ion or atoms are is very important when we're looking at mechanisms in organic chemistry or other kinds of chemistry.